In this session, I'm going to talk about setup time. Setup time is the same as setup cost. Setup time is related to capacity. Setup cost, as we have learned up to now, is related to inventory. Indeed, setup time also has a cost because each production time can be translated into cost. So this setup time can be also considered as setup cost. But the difference is this setup time is related to production and capacity. That setup cost is related to inventory. So each time we produce a batch of product, it takes some time. During that time, we produce Q units, and this Q is something that we need to decide upon. But then, because I spend this much time on producing this many units, this total time is added to the actual time of producing each part or handling each activity. The larger the Q, the smaller the S divided by Q. So if at the beginning of the day or at the beginning of the period, I set up the machine, produce whatever I need, and then go and set up for the next product and produce whatever I need, my capacity would be larger compared to switching frequently from one product to the other. But the same as the concept that we discussed in inventory, if I just set up and produce a lot of product, flow time will go up because inventory will go up, average inventory will go up. And among all costs of inventory, one of them is it is possible that I produce a defective product and continue producing it because I'm going to produce all of it and then go to the next product. And after I'm done with the next product, I'm going to put these two on the top of each other, assemble them together, perhaps. And then if I find that there is a mistake in production, then I should rework on a large number of products. So usually we prefer not to set up and produce whatever is needed, except for two stations, bottlenecks and the stations which feed the bottlenecks. In those stations, we really do not want to lose the opportunity of producing one single product. I will go through some examples and I think the issue will become a little bit more clear. So we are producing two products, product A and product D. We need the same number of these two products. Each unit of product A takes 10 minutes. Each unit of product D takes, and these are what we know them as TP. Each time we set up for product A, we need to spend 30 minutes. Each time we set up for product D, again we need to spend 30 minutes. We work 8 hours per day. What is the maximum capacity of this system? How much can we produce per day? The maximum number of units of A and B can be produced, and we need the same number of A's and B's. Perhaps they will go together and they will go on another part or join another part. So I need 30 minutes setup time for product A. I set it up and produce whatever I need, and then I need 30 minutes setup time for product B, set it up and produce whatever I need. The total of these two is 60 minutes. A day is 8 hours times 60 is 480 minutes. 60 minutes of it goes for setup time. I will have 420 minutes. 1A needs 10 minutes. 1D needs 20 minutes. So 1A plus 1D needs 10 plus 20, which is 30 minutes. 420 divided by 30, 14 units. That is 14A plus 14B. Maximum production capacity per day. We cannot do better than this. Now suppose we want to produce 2 units of each product, then switch to the next one. 2 units of each product, then switch to the next one. Each time we want to produce the combination of these 2 products, 30 minutes setup time for product A, 30 minutes setup time for product B, 10 plus 20 minutes for producing 1 product of each, multiplied by 2. That is equal to 120 minutes. So for each pair of 2 products, I need 120 minutes. In a day, I have 480 minutes divided by 120 is equal to 4. 4 what? 4 2A plus 2B. And therefore I have 8A plus 8B. I could have come here and said this is for 2 products of each. I divide 120 by 2, that is 60. Therefore, I need, on average, I need 60 minutes to produce 1A and 1B. 480 divided by 60 is equal to 8. That is 8A plus 8B. When I produce everything that I need and then I switch, my inventory would be 14 product of each divided by 2. That is 7 times 2, because I have 7 of each product. On average, I have 14 units of inventory. But when I produce 2 units of A and 2 units of B, that is 2 divided by 2, which is average inventory of each. And because I have 2 of each, that would be 2 units of inventory. Here, on average, I have 2 units of inventory. Here, on average, I have 14 units of inventory. If I make a mistake in those 14 units, then I need to rework on 14 units. If I make a mistake on those 2 units, then I just need to rework on 2 units. But don't forget, if it is the bottleneck or it is the station which fits the bottleneck, we really don't want to risk any capacity. We want to make sure that the bottleneck is utilized at full capacity, and the station before the bottleneck, the station upstream the bottleneck, will never go under a capacity less than what the bottleneck needs. How solve this problem? First, only focus on resource A. Resource A does 2 activities, activity A1 and activity A2. Setup time for activity A1 is 60 minutes, setup time for activity 2 is also 60 minutes. Production time for each of them is 1 minute. TPA1, time to produce A1, is equal to TP for A2, and it's equal to 1 minute per part. When we switch, there are 30 minutes switch time, setup time. Volume of the production of the two parts should be equal. A day is 8 hours. This is the best we can do. Setup time of product A1 is 60 minutes. 60 minutes. They both together need 120 minutes. A day is 8 multiplied by 60 equal to 480 minutes minus 120 minutes is 360 minutes. 1 unit of A1 needs 1 minute, 1 unit of A2 needs 1 minute, they both together need 2 minutes. Available time 360, time for each one 2, we can produce 180 A1 and 180 A2. This is the maximum capacity. Average inventory of each one, 180 divided by 2, 180 divided by 2. This is the maximum capacity and average inventory. 120 setup time, 360 minutes available time, 2 minutes for each pair of products, 180 pairs of product per day, that is 180 A1 and 180 A2. If I want hourly capacity, a day is 8 hours, I can define 180 by 8, which gives me 22 and a half product A1, 22 and a half product A2. So that's capacity per hour, but don't forget the inventory is still half of 180 and half of 180, because we set the machine and produce everything. It is not that we produce 22 units and then switch to the other. But that average still has a meaning. Now compute the capacity if they are produced in batches of 60 units, 60 A1, 60 A2. Setup times are 60 minutes plus 60 minutes. So that is 120 minutes over there. Production time is 1 minute for 60 units each, plus 1 minute for each of the 60 units, and that is 120. If we add these two together, that is 240. 240 units for 60, for production of 60 units. So that is 4 per pair. And a day is 480 units divided by 4 is 120. So if we produce at batch of 60, our capacity will come down from 180 to 120. That is the impact on capacity. It comes out from 180 down to 120. But over there, I produce 180 and then consume it throughout the day. Average was 90 for each product. Here, each time I produce 60 and then it goes down to 0. Average here is 30 per product. 30 compared to 9. Here, if I make a mistake and I find it out later, I should rework 180 units. Here, if I find a mistake, I should rework 60 units. That is the trade-off. Again, don't forget, on bottleneck, always try to have the maximum production, because each unit lost at bottleneck is lost at total system. Also, in the stations which feed the bottleneck, make sure they never leave the bottleneck hungry. The term that is used is starvation. Don't lead the bottleneck to starve. Always have product to feed the bottleneck. There are two terms, starvation and blocking. Starvation is when a station is waiting for input and the upstream station has not provided it, or the raw material is not available there. Blockage or blocking is when the product is completed in this station, but there is no room in the inventory of the next station to put it over there. Both of these things may have impact on throughput. Starvation, the station is waiting for input from the upstream station. Blockage, the station is blocked because the output cannot be placed in the downstream station. Batches of 60 units for product A. For 60 units of product A, we need 60 minutes setup time plus 60 times 1, 60 minutes operations time, 120. For product A2, we need 60 minutes again for setup time and 60 times 1 for production time, 120 plus 120, 240 for 60 A1 and 60 A2. We produce 60 units in 240 minutes. Therefore, capacity RP is 60 divided by 240 for 1A1 and 1A2. That is 0.25 A1 and 0.25 A2 per minute. When you multiply it by 60, that is 15 per hour. And if you multiply 15 by 8 hours per day, you get the same 120 A1 and 120 A2 per day. And because you are producing in batches of 60, average inventory of each product would be 60 divided by 2, which is 30. Suppose these parts go to resource D. Setup time of resource D or resource pool D is 0, suppose. Production time is 10 minutes. For the time being, suppose there is only one resource in resource pool D. Therefore, activity D will have a capacity 1 over 10 per minute. And its cycle time would be 10 minutes. Every 10 minutes, one product D can go out. Now, what should I do to balance the capacity of these two resource pools, resource pool A and resource pool D? Cycle time of resource D, I know it is 10 minutes. Every 10 minutes, one product D can go out, one part D can go out. Now I should make sure that the first station, station A, can also send one part out, one part A1 and one part A2 per minute. Let's see how it can be done. 60 plus 60 is setup time. This should be divided by Q. Q is the number of units in the batch. And this should be added to 1 minute for 1 unit of product A1 and 1 minute of 1 unit of product A2. Therefore, the total cycle time, average cycle time for producing 1A and 1B to be able to be added to D. Therefore, the average cycle time to produce 1A1 and 1A2 to go and be, for example, assembled with D is 60 plus 60, which is 120, divided by Q, plus the actual production time of those two. And that would be 120 divided by Q plus 2. That is the cycle time of a resource pool to produce 1A1 and 1A2 to be added to D and form a component or whatever. Cycle time of station D was 10 minutes. If I take that 2 to the other side, it will become 8 equal to 120 divided by Q. That means 8Q is equal to 120, and therefore Q is equal to 15. Therefore, in order to match capacity of resource A with capacity of resource D, I need to produce at batches of 15 units. 15 units A, 15 units B. 120 plus 2Q minutes to produce QA1 plus QA2. The average cycle time to produce 1A1 and 1A2 would be 120 plus 2Q divided by Q, which is 2 plus 120 divided by Q. This is cycle time of A1 and A2, which should be equal to cycle time of D. 2 plus 120 divided by Q equal to 10, and therefore the batch size is 15. 15A1 and 15A2. Now suppose we have added a new resource to resource D. Therefore, capacity of that station is not 6 per hour anymore, it is 12 per hour. Cycle time was 10, now because I have two resources, cycle time becomes 5. Don't forget, RP is equal to C divided by TP. Cycle time is 1 over RP. And therefore, it is equal to TP divided by C. Now, if I have two stations and TP was 10, cycle time is 5. We really don't need these computations. If I have one resource, I produce one product every 10 minutes. If I have two resources, I have one product every 10 minutes and another product every 10 minutes. So I have two products every 10 minutes. So on average, I have one product every 5 minutes, and that is the cycle time. Therefore, the process is quite the same. Over there, I had 2 plus 120 divided by Q equal to 10. Now I have 2 plus 120, exactly the same as what I had over there, divided by Q, equal to not 10 but 5. That means 120 divided by Q is equal to 3, and therefore Q is equal to 40. I need to produce in batch of 40s. So that was computation based on cycle time. If you are not comfortable with cycle time and you want to go through throughput, that is still valid, but computations are a little bit unnecessary. I have called it difficult, but it is not difficult. It's a little bit unnecessary, but I have elaborated here also. How much time do you produce to Q? How much time do you need to produce Q units of each of the two products? And what is the throughput, you need 120 minutes plus 2Q to produce Q units of product. That is the time that you need. If you divide it by Q, that will give you the TP. But 1 divided by that is 1 divided by TP is RP. Therefore, if you divide 1 by this, you will get the reverse. And that is your throughput Q divided by 120 plus 2Q. And then throughput of the two should be equal to each other. This is throughput of this station. Throughput of the other one is 1/10 per minute in the first case and 1/5 per minute in the second. So all of these lead to the same results, but the previous approach, in this approach, we first reverse something and then re-reverse it. Not needed. That concludes our discussion. Thank you very much for paying attention.